Hello everyone, this is Kang from Tsinghua University, presenting our findings on accelerating graph random walk. This work was mostly done when I was a research intern at Qatar Computing Research Institute in collaboration with my mentors both there and back in Tsinghua. First, what is graph random walk? Its input includes a graph and a set of workers placed at their starting vertices. During the walk, each worker walks around by randomly selecting an edge to follow. This lasts for a given number of steps until a given termination condition is met. Graph random walk forms the basis of many widely used algorithms today, which in turn have diverse applications, from link prediction for use cases like recommendation to graph neural networks and epidemic studies. Today, a major consumer of graph random walk results is graph embedding, typically running on GPUs due to its regular nature of performing matrix computation. The random walk computation feeding such embedding training with sample passes, on the other hand, is less regular, relatively heavy with integer operations, and requires large memory capacity, so it's typically done on the CPU side. With graph getting larger and GPUs getting further ahead in speed, graph random walk easily becomes a bottleneck. For example, a recent production system of Tencent reports reusing edge samples 10 times on the embedding side. The major challenge here is the random accesses dominating the graph random walk computation, with common graph processing tasks such as BFS or shortest path. An active vertex usually traverses all its edges in one iteration. Random walks, however, follow a random single edge at a time. Existing systems, therefore, took for granted that with random walk comes random memory accesses. The common design is to process workers in turn wherever they are. In this example, the green worker is at this vertex with 3 edges. It throws a dice and picks one, then updates its location to its new stop. Same thing for the other workers. This leads to two things. First, there is a high data dependency, so not only the accesses are random, we suffer from pointer chasing. Second, every time data are brought into cache, we have the entire cache line whose common size of 64 bytes can hold 16 edges. With computation scheduled by workers, it's highly unlikely any of the other 15 edges get to be used before the cache line is evicted, so most of the contents brought into the cache are wasted. This table gives the read latency along the CPU memory hierarchy, where we can see sequential accesses are quite cheap, even when we go to another NUMA node. Random reads, on the other hand, sees a sharp increase from L3 cache to the main memory. For pointer chasing, even L3 cache reads are expensive, and local or remote accesses are simply nightmares. With existing graph random walk systems, the major memory access types are exactly undesirable cases. In this work, we found that random walk don't imply random memory accesses. Actually, there are plenty of temporal and spatial locality if we look carefully enough. The key insight is that vertices are not created equal. Here we have the degree distribution of the largest real-world graph used in our evaluation. From Yahoo, with 700 million vertices, we sort them by degree and plot the average degree of each 1% group, confirming the well-known power law degree distribution. Though the average is only around 1,000, the degrees within the first few groups vary a lot, with the highest degree vertex having over 7 million edges. Meanwhile, half of the vertices have a degree under 8, and about half of those have only 1 or 2 edges. In graph random walk, the frequency of a vertex being visited is highly correlated with its degree, as shown by red curve. This means that on the spectrum of vertices by the degree, we have extremely popular and crowded places on the left, like a traffic hub in Manhattan. On the right, we have the silent majority, places like the Himalayas, where a spot is visited once in a long while. Our new system, FlashMob, is motivated by such disparity. For the high-degree vertices, which host the majority of workers, many strangers would happen to be on the same node, and we optimize by batching and pre-sampling PS. Rather than having each worker independently draw one edge at a time, we pre-sample many edges in advance to prepare for the large crowd. For example, this high-degree vertex V edge has a long edge list, and during pre-sampling, we throw a dice for thousands of times, saving sampled edges in a pre-sampled edge buffer, which will be consumed sequentially by thousands of workers. Due to the buffer space requirement, each vertex partition at the left end contains a small number of vertices. Obviously, such pre-sampling is another round of computation, but that's completely justified. In the pre-sample stage, we do have to do random accesses, but this process focuses on one vertex at a time, where the edge list typically fits into the L2 or even L1 cache. In the work stage, where the worker's locations get updated by following a sampled edge, the workers access the pre-sample edge buffer only in a streaming manner, bringing little wastage of cache line data. For the Himalayas on the right side, doing pre-sampling brings no benefit, as the vertex would be lucky to be visited at all, and we stay with direct sampling DS. However, we find other ways to save big here. Recall that a huge number of low-degree vertices have a common degree. For example, this dual-edge vertex VL has many 2-degree companions. FlashMob packs them tightly, so here one vertex partition can hold many vertices, with each worker sampling for itself randomly. Memory accesses are slower, but there are fewer of them. First, there is no pre-sampling stage. Then, with uniform degree partitions, we get rid of the degree lookup forced by the common CSR data structure and index to any edge list with simple arithmetic, which reduces memory accesses by half. Finally, we fit more vertices in a partition, containing all random accesses within a certain cache level if the partition is small enough. The hard problem is where we should switch between these two sampling strategies and how we should cut the spectrum into partitions, which form the basic work unit for FlashMob. We want such partitioning to be automatic, adaptive to the CPU architecture, resource configuration, and input graph. More specifically, we need to optimize in a 2D solution space with 4 candidate partition sizes cut to fit the L1, L2, or L3 caches, or what we call DRAM size, as once it's beyond L3 it doesn't matter much, and 2 candidate sampling policies PS or DS. Fortunately, we found this maps well to an existing optimization problem called MCKP, multi-choice knapsack problem. It is NP-hard but has a pseudo-polynomial dynamic programming solution. We won't have time to get into the details here. Please check it out in the paper if you are interested, along with a few other optimizations, such as our cache-aware shuffling and NUMA-related work strategies. We evaluated FlashMob on a QCRI server with this configuration and compared it to 2 baselines, including our own NetKing, a graph random walk engine, and GraphFit, a graph embedding framework with CPU-side random walk and GPU-side training. We tested on these 5 real-world graphs with very different sizes. Compared to NetKing, the stronger of the 2 baselines, FlashMob is significantly faster on both of the work algorithms evaluated, bringing a 4 to 20 times speed up. Again, due to time limit, we choose to show a performance highlight using 3 toy graphs designed to fit into L1, L2, and L3 caches, plus YouTube and Yahoo, the smallest and largest graphs among those tested. With NetKing, the per-step work time shown in nanoseconds keeps growing as the graph gets larger. With FlashMob, on the other hand, the 2 real graphs with 3 orders of magnitude difference have much closer performance. And even with the 58 GB Yahoo graph, its per-step work time beats NetKing's with a 5 KB toy dataset. To summarize, the foremost takeaway from this work is that graph random walk is not as random as one might think, and we can create locality by a few tricks: partitioning, batching, reordering, and scheduling. As a result, all our memory accesses are staying with the more pleasant areas in this latency table, and many techniques introduced here can also be applied to other graph sampling algorithms. Secondly, the table reminds us again that with today's CPU architecture, sequential accesses are much cheaper. This is reflected in FlashMob's design, where we trade volume for speed, and find that doing more scans often saves both time and actual memory traffic. Finally, we argue that old-fashioned white box optimization still works and provides a lightweight alternative to machine learning-based system auto-configuration. In our system, the one-time profiling takes around 200 seconds, and the MCKP-based optimization takes less than 1 second, as compared to the much more time-consuming random walks. For more details, please watch our 20 minutes video or refer to our paper and the artifact on the GitHub. Thank you.